Thank you. First of all, I want to thank all of you for coming, and I want to thank the organizers, of which I was one, for the opportunity to be here. But it was, I really enjoyed the meeting, I've enjoyed the talks, and I've enjoyed the discussions. I wish sometimes there would have been more time for them, but I understand, you know, we want to make sure everybody gets a chance to have their say. Today I'm going to talk about something that hasn't been talked about at this meeting very much, and that is about peptides and proteins. Perhaps it's important to note that much of the chemistry of small molecules that was developed in the first 2 billion years of evolution was dropped when multicellular life developed. If you take animal life, there's virtually no synthesis, just a few of terpenes, alkaloids, steroids, and so forth. And as a result, it's not surprising that most of our drugs are problematic. And so eventually, if we're going to mimic nature, which is what we're presumably trying to do when we treat disease, we have to use what nature uses, which are mostly peptides and proteins and nucleic acids to modulate biological function, at least in our life, human life. So that's the first thing I'd like to say in terms of a general thing. The second thing is, when disease occurs, there are many changes that occur in the expressed genome. Now, when there's not disease, there also are changes in the expressed genome. So the question is, which ones of the changes in the expressed genome are important and which ones aren't? How do we find out? How do we know? Well, these are very difficult problems to answer, but I think what we have learned, at least in the last 15 or 20 years, is that monovalency, which has been the major way in which people have approached drug design, is inadequate. So I hope to talk about that and how we use multivalency as a way to try to examine some of these problems. Before I start, I want to thank the people who did this work. It's a very interactive group in 3 different locations now. Bob Gilley started at the University of Arizona, but then he moved to Moffitt, and we are collaborating with the group in France. And most of the work I'm going to talk today about were done by Joseph Wagner, Jatinder Joseph, Nabila Brebez, and Professor Ron Lynch, and Professor Min-Ying Kai. Ron Lynch is in a different department than we are, but the other people are in chemistry and biochemistry. So what is the problem? So as we know, current approaches for treatment of our major diseases have been disappointing. And I'm talking here about degenerative diseases, not about diseases of bacteria and so forth. Although those are disappointing because of the way that we've used them. I won't say more about that here, except to say that we have done a very bad job of treating these diseases too because of the way we have used our antibiotics. But problems in all of these cases, problems of toxicity, tolerance, abuse, are ubiquitous, and also, of course, many of our drugs cause death if you take too much. So the questions, are we looking in the right place with the right paradigm for design? And, you know, Paul Ehrlich was a very, very smart man, but he was wrong. There are very few magic bullets. That's not the way nature works. We've learned that. Paul didn't know that. But we've used his paradigm now for over 100 years of drug design, and it's been inadequate. So even though he was very smart and had really great ideas, we have to move on. You know, even the best ideas are contingent on what we learn, right? So hopefully we're learning something as we move ahead. So in these disease states, the degenerative diseases such as chronic pain, cancer, diabetes, addiction, CNS diseases, and so forth, there are changes in the expressed genome that are related to our treatments. And so drug design must consider these because these are systems changes. They're changes in the way in which the expressed genome is expressed. Systems, not just one little molecule changing here or one little protein changing there. It's not the way it works. So we have this increased complexity that we have to consider. And so we thought, well, one of the ways we can do it is increase the complexity of our drugs. But we have to do this in a very careful way in order to avoid these other problems of toxicity that come up, which are present in all of our current drugs, or virtually all of them. So, but we think advantage can be taken of this, and I don't have time to talk about all the things I promised in my abstract, so I'm just going to concentrate on cancer detection today in the question of time, trying to stay on time, which is always very difficult for me. But anyway, so these new paradigms, we know that now that cancer is a multifactorial disease in which many, many changes occur in the expressed genome, both upregulation and downregulation. We're going to target primarily upregulation. Now, there's lots of changes. Some of them appear to be, from what we know so far, critical to disease, and some don't appear to be. But we don't really know. We just can measure certain things. Remember what we do in science? We study what we can measure. And unfortunately, we may not be measuring the right things. And if you've been in science as long as I have, we know that we haven't been measuring the right things 30 years ago, and now we do better. But we're still learning, right? We have lots to learn. So we have chosen to specifically target, we don't care which ones are critical or not. We just want to know the ones that have changed a lot. So we can target those with multivalency. And so this is primarily the way that we've approached this. We haven't asked ourselves the question, well, what's important for the disease? Now, in some cases, we found out that what we chose was important for the disease. In some cases, it wasn't. But that, in either case, it allowed us to do the detection. So that's the key that I want to emphasize in this talk. Oh, I'm sorry. So we're going to target cell surface proteins, membrane proteins. So what's the advantages of doing this? Well, first of all, the chemical doesn't have to get into the cell. However, there are proteins on the cell surface that do get into the cell. So if we want to put our drug into the cell and use a pro-drug approach, we can do that if we choose the right proteins on the cell surface. That is, those that can be internalized. And there are quite a few, there are classes of membrane proteins that can be internalized. And then, of course, the nice thing also about this is, everything I'm going to talk about, there was lots of SAR before we ever started on this for the individual things. Now, there's a problem with multivalency that you have to consider, and that is that each of the targets you have to independently target from each other, and they cannot interfere with each other when they do this. Now, in the case of what we're doing with cancer, where we want to cross-link receptors, this is easy. We just separate them by a lot. But in many other cases that we've studied, which I won't have time to talk about today, you have to have overlapping pharmacophores that don't interfere with the other receptors and so forth. This creates a problem of design that's different than the problems of design that we generally have considered in the past. And so there's lots of failures if you look at what people in industry have tried. We've been very successful because one nice thing about peptides are they almost all biologically active peptides that I'm knowledgeable about have ancillary sites that are not involved in the interactions with the protein. And you can use those to put on reporter groups and put on a second pharmacophore and so on and so forth. But you have to study this very carefully before you do this. Okay, so the idea is very simple. Here's a healthy cell, here's a normal cell, here's the ligand that we produce, in this case trivalent ligand. In this case there's only one receptor that is expressed on the cell surface, but in this cancer cell there are a couple of others. And so the idea is by using multivalency that you have two things that can happen, right? You can cross-link them if you separate them properly, and then after you cross-link them, you get synergy. Now, Delbruck studied this and reported on this. The great thing about cell surface proteins also is the reduction in dimensionality. You're now in a two-dimensional environment instead of a three-dimensional environment. This has a tremendous kinetic advantage, not a thermodynamic so much, but a tremendous kinetic advantage. And people really haven't taken most of everything you hear people talk about drug design, they talk about the thermodynamic properties and very little about the kinetic properties. But in this case, they're extremely important because the kinetic effect is what you really want to get. And Delbruck said it could be as much as 10 to the 6th. So it's pretty amazing compared to what you can do inside the cell if you think about it a little bit. Okay, so we don't have to get, oh, I'm sorry, I'm going in the wrong direction here. So, okay, so we started with polymers in this back in the 90s, and we were able to prepare a polymer with polyvinyl alcohol polymers that had the ligands on them, in this case a melanocortin analog, MSH analog that was stable, and then we had a reporter group, a fluorescent reporter group. And we made this peptide here, this ligand that recognizes the protein that's on the cell surface. We made very small particles, silicon particles, and you can see that they bind to the cell in this electron micrograph. Or you can make very large, the things that we usually use for solid phase synthesis, and the cells will be attracted, those that are cancer cells and those that aren't attracted to these polymers. And you can even study what happens to these polymers. They get internalized, and if you watch for long enough, you can see where they go to in the cell by blowing this up, but you can see them coming back on the cell surface 5 hours later. And we've done all those kinds of work and published. These are 2 of the 7 or 8 papers we published in this area if you're interested in this. So we thought that at least that gave us a hope that we could do this sort of thing by design rather than just making a random polymer and hoping that randomness would do the job. And it did do a pretty good job, but not the kind of job we'd like to do. Now, first of all, if you're going to make linkers, you have to ask yourself about both thermodynamics and kinetics again. How much flexibility do you want? Is flexibility important? How important? How rigid can you get? So I'm going to tell you what we found, because I don't have time to give you the data here today. But if you have something very rigid like this molecule here, which still has rotation about single bonds, but it's too rigid, and you don't get any synergy at all. This is what we found. So I'm not going to give you any of that data, but I'm just telling you if you want to know. But semi-rigid is very good. So collagen-like structures are extremely good. Collagen is useful in biology for a very good reason, because it can change its conformation when necessary. Okay? And then, of course, Pego is very flexible, but allows you to do a lot of nice chemistry, so you can attach functional groups and reporter groups and so forth in doing this kind of research. We also then did, this is before the days of any X-ray crystal structures except for rhodopsin, and so we did some modeling based on our models for the receptors we were working with and were interested in targeting in cancer cells. And what we found is that the separation you want between the 2 pharmacophores is between 25 and 50 angstroms. That's what we predicted. It turns out that in most cases so far that we've studied, and there's been a few other studies now also reported in literature, that actually it's closer to 20 to 30 angstrom than to 40 to 50 in most cases, but not in all. So it just very much depends upon how the 2 receptors, different receptors, can position themselves next to each other. And that, of course, we don't know anything about. I wish we have a method to do that, but we can't get any funding to do it. I've been trying for 5 years. So anyway, that's another problem in our science nowadays. You can't do anything new that might fail, right? I mean, until you succeed, you can't get any money to do anything. And this turns out to be something reasonably expensive to do because it's very time-consuming, so you need people dedicated to it. So you at least have to have money to pay somebody, to a postdoc or a graduate student or something to do this. Anyway. So that's just a complaint. I'm sorry to bring up my complaints about what's happening in science these days, but since I'm an old man, I'm allowed to do that. Anyway, so here's the kinds of constructs that we've made. So as I said, we have this pro-gly residues, and we have various numbers of them that we've done here. We have our Pego that we use for various purposes to attach things to them to give us this flexibility. And so here's the combinations, the combinatorials that we used in our synthesis. Now I have to point out something very important. You can only do this with certain kinds of chemistry. I don't know if you guys know that the most optimized chemistry is Bach peptide chemistry. You can make a 50 amino acid peptide that you've optimized. You can make it. That's, depending upon the chemistry you use, that's about 70 organic chemistry steps. And you can make it with an average yield per step 99%. So most of our peptides that we're making here, our conjugates, are 30 to 60 steps of synthesis. Okay? And I think you will agree, if I show you the HPLCs, that we do a pretty damn good job of optimizing this. So we get about a 50% yield in these syntheses. This is an HPLC of a crude preparation. So we have optimized the chemistry for this. We aren't the persons who developed all the optimization procedures, but they are there in the literature. And if you want to take the time, which Jatinder did, you can optimize these kinds of conjugations very well. And this is a really big opportunity that isn't realized in most of the other chemistries we have out there in organic chemistry, that people aren't realizing. You can also do this, by the way, with nucleic acids, in case you're interested in knowing that. Okay, so now, once we have these things, I don't know why it's not going forward or backwards anymore. Pardon?
Just click on sign up.
I have to click on something else here now? Sorry. Just hit control or something? Oh, I'm sorry. Thank you. Okay, so here's what we found. Now, first of all, note that in these, we did scattered plots in these cancer things. I'm sorry, I'm going to have to move very quickly now. We did scatter plots to find out what the concentration of these receptors were in these cancer cell preparations, and you can see in this case the CCK receptors in much higher concentration than human. So we got the synergy here, and there's good reasons for this. I don't have time to explain it, but you can read our papers and find out why you get only synergy at the least common receptor. And this seems to be true, and we usually get about synergies of about 50 to 100-fold. This is what we usually get. But here's what's really exciting. When you do this in live cells, or you do this in vivo. Okay? The binding constants for these, as you saw, are in the nanomolar range when they're binding to both. Okay? When they're binding to only one, they're in the micromolar range. So, in the binding to only one, they have an off rate that's fast, right? Minutes. Within 3 minutes, you cross-link. When you only have one of these receptors, you don't cross-link, right? And so you see nothing after 3 minutes. And if you gain this up, you see they're starting to bind, but here it's overwhelmingly bound. 3 minutes, okay? Cross-linking. You can only do this by cross-linking. You get this tremendous kinetic advantage that Delbruck talked about 30 years ago. It's fantastic. I mean, you know, whether you do this with the ligands with the lower, that has a higher concentration, lower concentration, in terms of what you can observe, you get the same result. It's really fantastic because of this tremendous kinetic advantage that you get. And so we're really excited about this aspect of it more than anything else in many ways. Well, when you go in vivo with this, let's see if we can, oh, we got to do this again. Apparently I'm touching some things wrong or something here. I don't know. Okay, there we go. Okay. So we've also done this with dendrimers, and I'm not going to go through this now because I've only got 3 or 4 minutes left to tell you about some. But we've done this also with dendrimers, and it turns out these kinds of dendrimers that we have, where we have multiple ligands that we can attach them to these by using the right kind of protection schemes. And again, we use primarily solid phase synthesis with these. These don't start with a peptide, but then you add the peptides to them and so forth to do this. And so this is just one result that we get the monomer, dimer, and trimer of these. These are homovalent now, not heterovalent. But you can see that you increase the potency of these things by a couple of orders of magnitude because of the synergy you get in the binding affinities now. This is the thermodynamics. The kinetics, of course, are very good as soon as you get to dimers or trimers. Okay, so this works in vivo. And, surprise, occasionally it actually kills cancer cells. And this is one of those choices. We didn't know this would happen, although there were clues in the literature from our own work that we had forgotten about. But when we did this tumoring for a melanoma tumor, you can see that when we left after just one day of treatment. We left it for 2 weeks. It was the Christmas holidays last year. When we came back, there was no tumor. So we're, of course, following up on this now with highly selective ligands for this particular tumor, this particular cancer. And we're pretty excited about the fact that in some cases, these multivalent ligands also kill cancer cells. We don't know why. Hopefully we can get some money to find out from our colleagues when we get in our grant preparation. So anyway, so what we've done is we made these multivalent ligands. We think we have the right separations of them now so we can cross-link, and we're going to keep on doing the work that we've been doing. We have a lot of work to do, obviously, in vivo and in vitro to continue this kind of work. So thank you very much for your attention. Happy to answer any questions.
So you were a little bit long, but I think you have a question
okay,
to continue the speech.
I love questions. They're more important than the answers.
Very interesting talk. I have a question. So you have two peptides, as two peptide ligands have with a link in the middle. How do you determine? So assuming the two peptide ligand will bind each their receptor on the cell surface, and how do you determine the distance between each other? I guess you probably have to optimize those.
Yeah. Well, as I said in the few slides that I showed about this, what we've done is we didn't know what the distance should be because nobody's been able to really measure these distances in any way on membrane proteins. So we had to do this modeling that we did and decide that the distances should be somewhere between 20 and 50 angstroms. And we found from our experience so far that most of the distances that we do when we get cross-linking is around 30 plus or minus 5 angstroms. But we've also had one case so far where you had to have separations by 50 angstroms in order to get cross-linking, at least that was kinetically advanced, like what we saw in the slides I showed you. So it's trial and error. We don't have, anybody who's trying to do this with membrane proteins knows that we don't have good enough information about structure to really do this properly.
Well, second question, a very short answer.
Okay, I'll try to keep. I'm sorry, I'm a talker.
Yeah, I think it was a great talk. So, quick question about the first and the second step. So, the first step is dynamically controlled. The second step is kinetically controlled. Once you've optimized the linker for the second kinetic step in your process for a bivalent or divalent scaffold, would you recommend optimizing the rigidity of the linker to increase the speed?
That is a terrifically good question, one that we asked ourselves when we started all this about a decade ago. No, because this is a really critical issue, because you have these arguments in the literature that have been going on for 50 years or longer about what is the relationship between rigidity, in other words, between the rigidity and flexibility in biological function. I mean, it's a very important question, but one in which, depending upon what you're doing, you have different answers. Our experiences, that's all we can give you so far, our experience, is that you want something between rigid and highly flexible. And that's the ones that work the best. The ones that we have shown, that I showed you, are the ones that have combinations of not highly rigid, semi-rigid, and flexible. And these are the ones that have worked for us. It's all empirical. We don't have any theory about this at the moment. But the tremendous kinetic advantage you have is really what I think is we have to really try to understand. Because if we can really predict that, then I think we have a really powerful way to do multivalency.